verbally. And as I said, the good part about a survey is you can collect data from a large number of people. You can do it quickly and cheap. All right, more types of research. Archival research uses past records or data sets to either answer questions or search for patterns or relationships. That's a real easy, cheap one to do because you can just go back and look at patterns from the past. But of course, the problem with archival research is you can't manipulate any of your variables. Longitudinal research are studies in which the same group of individuals is surveyed or measured repeatedly over an extended period of time. So I might study the same group or cohort of children starting from preschool, and then I'll interview them again every year all the way up until college to see how certain people change over time, right? Perhaps my hypothesis is that children who come from divorced homes may not perform as well in school, right? If that's my hypothesis, it would be a good idea to look at them over time as opposed to just at one period of time. The problem with longitudinal research, however, or one problem with it, is attrition. Attrition is the reduction in the number of research participants. It's when they drop out. In a lot of medical research, the problem is that the patients can often pass away, right? If they're working with terminally ill or very ill patients, they lose a lot of patients because they pass away. In psychology, it's more that they can't be bothered to come back, or they found the survey too long and annoying the first time, so they don't do the second time. But anyway, attrition is when you lose people because of dropouts, and that's a problem with longitudinal research. In that situation, if you're worried about attrition, you might be better off doing cross-sectional research. Cross-sectional research compares multiple segments of population at one time. So with longitudinal research, I would follow that same group of kids from preschool all the way up through high school, whereas with cross-sectional research, I would interview some preschool kids, some different kindergarten kids, some different first grade kids. I interview them all now this year and compare the data that way. So as the chart shows at the bottom, the difference between cross-sectional and longitudinal research, the main difference is that cross-sectional all happens at one point of time with different samples and gives you a snapshot of that point in time. Whereas longitudinal research measures or collects data from several points in time using the same sample and looks at change at an individual level instead of at a more societal level. The last type of research we'll be discussing is correlational research. This cannot be said enough. While correlation is a very good kind of data collection, a very good kind of research, it does not determine causality. That means as you can look at if things are related to each other. Correlational research tells us some very interesting things about relationships between variables, but it never allows us to determine that one variable is causing a change in the other variable. And the reason for that is that we're not manipulating anything. We're just looking at it in a natural setting as it occurs. Let's talk about what it means a little bit, and perhaps it'll make more sense. Correlation is a relationship between two or more variables, and when two variables are correlated, that means one variable changes as the other one does. But as I said, correlation does not mean causation. Let's pause real quick and look at the picture at the bottom. You can see that height and weight have a positive correlation. Those dots are all going up sort of in almost a straight line. What that tells us is that people who are taller weigh more and people who weigh more are taller, but it doesn't mean causation. It doesn't mean that being tall makes you weigh more or that weighing more makes you tall, right? It does not mean causation. It just means that they're related to each other. A confounding variable is an outside factor that affects both of the variables you're looking at. The example they give in the book is they found that amounts of ice cream eaten and crimes committed are highly correlated. So what that means is the more ice cream being eaten in a given month, the more crimes are committed that month. Of course, eating ice cream doesn't cause people to commit crimes, and committing crimes doesn't cause people to eat ice cream. What happened in this case is there was a confounding variable, which was the warm weather. During months with warm weather, people commit more crimes And during months with warm weather, people eat more ice cream. So those two things can be correlated without having any actual relationship to each other. And that happens with a confounding variable. I'm going to skip real quick to the illusory correlations because those are similar to a confounding variable, but the confounding variable is a real correlation caused by something else. Illusory correlations are not correlated at all. It's just things people believe or think are correlated based on their confirmation bias or their selective attention that they think something is correlated. For example, the month that you were born in and your personality. But research has shown time and time again that those things are not actually correlated. I'll go back up to the correlation coefficient, which I'm going to discuss more on the next page. It's often referred to as R, and it's a number between -1 and +1, so it's usually a decimal, which indicates the strength and the direction of the relationship between variables. So this first example, A, has a positive correlation between height and weight. It's pretty close to being a straight line, and it goes up, meaning as one variable goes up, so does the other, right? As height goes up, weight goes up. So that means it's a positive relationship, and being that it's pretty straight, it's pretty close to 1. So I would guess that this one's maybe a 0.9 or a 0.88. If you look at the tiredness one, or B, has a negative correlation. This time we can see that hours of sleep and tiredness are negatively correlated, which means the more sleep you get, the less tired you are, right? We might think that we know there's causation in here, but remember, correlation does not equal causation. We don't know for sure just by looking at this correlation that sleeping more makes you less tired. However, it is a negative correlation. It's maybe not quite as strong as our first correlation, so I'm going to guess this one would be maybe a -0.7, 0.75 or something. And then the last one shows no correlation. They measured people's shoe size compared to their hours of sleep and saw no correlation at all between the amount of sleep somebody gets and the size of their feet. So this would be a 0 correlation. Let's look at these other examples. The top one is a 0.92. It's a very strong positive correlation. A weak positive correlation might be a 0.58. Next to that is a strong negative correlation. So the first one and the third one that are both 0.92, it's the same level of correlation, just one of them is positively correlated and one of them is negatively correlated. Meaning one of them, as one variable goes up, the other one goes up. But for the red one, as one variable goes up, the other one goes down. That's a negative correlation, but it's still a strong correlation. In the bottom row, we see a weak negative correlation with an R value of -0.6, and then a moderate negative correlation with an R value of -0.84, and then no correlation at all, very, very close to 0, 0.04. The two variables in this study were not correlated at all. So those are your R values, some examples there. Now let's discuss real experiments. We kept talking about how correlation does not mean causation. We cannot determine a cause and effect relationship from a correlational study. Correlation and causation do not go together. They're still very valuable studies, but if we want a cause and effect relationship, if we want to know that one thing causes the other, we need to use an experiment. So we're going to discuss experimental design because designing a true experiment is the only way to determine a cause and effect relationship. A cause and effect relationship is defined as the changes in one variable causing changes in the other variable. And like I said, it can be determined only through an experimental research design. So that's a big difference between correlational studies and experiments is that the experiments are the only ones that can determine the cause and effect relationship. In order to conduct an experiment, you'll need operational definitions. Those are descriptions of the actions and operations that will be used to measure the dependent variables and to manipulate the independent variables. To be a real true experiment, the independent variable needs to be manipulated by the researcher. Quasi-experiments are things where the independent variable is something like age or gender which can still be randomized by the experimenters, but it can't be manipulated, right? The experimenter cannot change your age or your gender. However, with a real experiment, we can manipulate the independent variable and measure the dependent variable, but we need to operationally define them, right? So if I'm saying that hours of sleep, the more somebody sleeps, the less tired they will be, how am I going to manipulate how much they sleep and measure how much they actually slept? And then how am I going to measure how tired they are, right? That one might be a little trickier. How do we measure how tired they are? Those are our operational definitions. The diagram with the pink and blue dots shows random selection and random assignment, which are two different things, and they're both important in experimental design. Your population is everybody you want to study. Sometimes it's everybody in the world or everybody in your country or your state. Sometimes it's everybody in 12th grade or everybody with a specific type of heart defect or everybody who's been divorced, or everybody in the whole population is who you're looking at studying. But of course you can't bring everybody in the whole population into your laboratory to study them. So we do what's called random selection. Random selection means that everybody in the population had an equal chance of being picked for your sample. You randomly pick them, meaning that it wasn't only people who want to be in your study. It wasn't only people who go to your school or live on your street. Everybody had an equal chance of being picked. Once your sample is picked, that sample represents your population because it was random. So most likely the sample you get represents the population. Then we take our sample and we use random assignment to split the people or the test subjects into two groups, the control group and the treatment or experimental group. Your book calls it the experimental group. Some people call it the treatment group. Basically, the control group doesn't get the thing that you're measuring the effect of, and the experimental group does. So in our picture on the right of the two plants, the experimental group gets water and the control group doesn't. In a real experiment, they would probably both get water, but the experimental group might get a special type of fertilizer or something in the water, right? If you don't give the plant any water, it'll die. But the experimental group gets what we're talking about or what we're measuring, what we're manipulating, and the control group is just there as a control to see what happens anyway without this treatment. In the case of a vaccine trial, they would give the experimental group a real vaccine and the control group a placebo vaccine and compare the differences between those two groups over time. Without the control group, you would have nothing to compare the experimental group to. So I just mentioned a placebo vaccine. Placebo effect is when people's expectations or beliefs influence the experience that they have. And it's quite interesting because it actually really works. A lot of the time when people take placebo medication or receive a placebo treatment, they're not actually getting anything. It's just a sugar pill and nothing. But it can work. It can have effects because they are expecting benefits. And their brain can literally release endorphins or dopamine to help with pain, or it can release different types of neurotransmitters or hormones depending on what you think you're receiving. And placebos can actually have quite a big effect. And that's why it's important to use placebos in an experimental design that has any type of medication or treatment. Because if you don't think you're getting the treatment, just thinking that you don't get it can make the difference between the two groups. So again, we split our main sample up into a control group and an experimental group, but often, when possible, the control group gets a placebo rather than just nothing, if that makes sense. One last thing in experimental design, I think this is the last thing, we'll talk about the difference between a single blind and a double blind study. It should always be single blind, at least single blind to be an experiment. What single blind means is that the people in the groups don't know which one is the control group and which one is the treatment group, right? If you know you're getting the placebo, then the placebo effect isn't gonna work, right? Nobody should know if they're in the control group or the experimental group. However, when it becomes double blind is when even the researcher doesn't know. And the reason for this is that observer bias we were talking about earlier, but this time it's called experimenter bias. Experimenter bias is when the experimenter is expecting something, so he sees things a little bit differently due to his expectations. That's why double-blind studies are the best when possible, that the person administering the treatment does not know which group is getting the real treatment and which one is getting the placebo. Obviously, it's written down somewhere. Somebody knows, but not the person who's administering it. So in that other picture here on the right, we see the experimenter is blind to who's in which group, and the participants are blind to who's in which group. So that would be a double-blind experiment. All right, this isn't really about experimental design, actually, but it's part of it. You've probably learned this in previous math classes, the independent versus dependent variables. The reason that this is important is that in an experiment, a true experiment, you can control the independent variable, which allows you to determine cause and effect. When you cannot control that independent variable, when it's something like somebody's age or the price of eggs at the store, and it's not something you can control, it becomes a quasi-experiment, as long as all the other aspects of an experiment are being met. Let's discuss real quick the difference between independent and dependent. The independent variable is the cause, the dependent is the effect. The independent variable comes before, and the dependent variable comes after. Sometimes they come kind of at the same time. The independent happens by itself, it's independent, and the dependent variable happens because of the independent, right? The dependent variable happens because of the independent variable. The independent one is independent. He's going to be on his own anyway. He is just going to keep on going. But the dependent variable literally depends on the independent one. And when you're graphing these relationships, the independent goes on the x-axis and dependent on the y-axis, though I don't think we're going to be doing any graphing. I want to do just a couple examples of independent and dependent variables to practice. Let's think about a dog's weight versus the dog's breed, right? There's definitely some correlation in here, but if we're actually measuring independent and dependent, we would probably say that the weight depends on the dog's breed, right? Although this would not be a true experiment since we cannot manipulate the independent, which is the dog's breed. Let's see if we can find any true experiments in here. Your grades versus time spent studying. That could be a true experiment because the time you spend studying is the independent variable and your grades depend on it. So the experimenter can manipulate the time that a student spends studying and then measure their grades. That would be a true experiment. Next one says the number of pieces in a puzzle versus the time it takes to complete the puzzle. This could also be a true experiment, right? The time it takes to complete the puzzle depends on the number of pieces in the puzzle, making the number of pieces the independent variable. Can it be manipulated? Yes. Experimenters can give different groups of people different puzzles with different numbers of pieces and see if the puzzles with more pieces take longer to complete. That would be a true experiment. The fourth one says the price of your car insurance versus how many accidents you've had. This one seems maybe even more like a correlation, but a lot of car insurance companies will raise your insurance when you have more accidents. Not going to be a true experiment because, of course, researchers cannot force people to have car accidents. As we'll talk about later with ethics, that would not be ethical. But we can measure it, right? We can see how many car accidents people have and then measure if their car insurance depends on it or not. The price would be dependent. And finally, the distance to be traveled versus the time to get there. This would probably be almost a linear relationship, as the time it takes to get there depends on the distance to be traveled. But of course, there's other factors in here like speed limits and traffic, right? But maybe we could do just running in a laboratory, right? And then the researchers could manipulate the distance that needs to be traveled, right? How far they need to run. And then they can measure how long it takes people. So that could be a true experiment as well. All right, moving on from independent and dependent, we're going to talk about reliability versus validity. Reliability asks, does what we're measuring yield consistent results? So remember we talked about operational definitions and how you need to actually define how you're going to measure something, right? So maybe I'm going to measure how tired somebody is by giving them a survey about how tired they feel, right? Perhaps I might also measure how many times they yawn while taking that survey. So reliability, does it yield consistent results? Do I find that more tired people really score higher on my tiredness quiz, right? If overall more tired people score higher and less tired people score lower, then that would mean it's consistent results. The validity, is the measure actually measuring what it's intended to measure? So I actually like these targets over here on the right side. Target A shows somebody who is shooting their bow and arrow, and they're not valid or reliable. If you look at those X's, they hit a different spot every time, and it was never the bullseye. Their shooting is neither valid nor reliable. In B, the shooter is valid but not reliable, meaning that they did hit the inner circle or the bullseye every time, but not exactly the same spot every time. It wasn't consistent, but it was still doing what it was supposed to do. At the bottom in C, we see one that's not valid, but it is reliable. They hit the same spot every time, but it wasn't where they were supposed to hit. And finally, D shows valid and reliable. They hit right where they were supposed to hit, and they hit the same time every time. I really like the book's example about the kitchen scale. If you have a scale that consistently measures everything a little bit heavier, let's say 5 ounces heavier than it's supposed to be, that's still reliable, right? It's very reliable. It measures every single thing you ever put on it at exactly 5 ounces more than it's supposed to. But it's not valid because it's not giving you the true weight of the item, right? That would be something that has reliability but not validity, right? Sometimes you could have validity that's measuring the right thing, but it's not reliable. It doesn't give you consistent results, either time after time or between different researchers or different experimenters. The book discusses a few different types of reliability and validity. I suggest you learn those. They're interesting and important. We will move on. We're almost done with this chapter, I promise. Let's talk about the last step of the scientific method, which is publishing or sharing your findings. When you conduct a real scientific experiment, most likely you will be affiliated with a university or a research company. You might want to publish your findings, or you probably will. And unlike an article that you might find published in a magazine, like Psychology Today, which targets a general audience, scientific journals publish peer-reviewed journal articles, which are aimed at an audience of professionals and scholars who are actively involved in research themselves. And as the arrow says, this is the type of article you should use for your term paper. You go to scholar.google.com and you can search all the journal articles. I believe the library has lots of resources as well. I can help you figure those out. But I love scholar.google.com. It leads to lots of peer-reviewed journal articles. So when it's peer-reviewed, what that means is that other researchers in the field, other scientists in the field, have read it before it was published and reviewed it. They are saying, does it make sense? Is it well written? Are there variables defined properly? Is their experiment set up like a true experiment? And peer review also ensures that the research is described clearly enough that other scientists could replicate it, right? For something to be valid, you need to be able to replicate it, meaning to do it again. Because if I cannot do your study again, then I can't be sure that I would get the same results as you, right? And I want to be able to replicate your study, get the same results, and then we'll really know that the hypothesis is true, right? After several people replicate. Finally, the American Psychological Association, also called the APA, they publish a manual detailing exactly how to write a paper to submit for scientific journals. If you want to write a peer-reviewed journal article, you'll definitely need to follow the APA guidelines down to a T. For your paper, you will also need to use APA format. You're mostly going to be looking at the in-text citations, the reference list, and the title page, since you're not writing a research report like they are with methods and data and all of that. Anyhow, we'll go over that for your term paper, but we are almost done. Let's talk about ethics, and then we will summarize. The IRB is the Institutional Review Board. Before you conduct your research, you need to write up a proposal, and, well, not you, but a researcher. Before the researcher conducts their research, they need to write up a proposal and send it to the IRB, and the IRB is going to approve it in terms of its ethics. They approve any kind of research that has human participants. So not just psychology, but any research that has human participants needs to be approved by the IRB in order to proceed. And two things that the IRB looks at, they look at a lot of things in terms of ethics, but two important issues are informed consent, which is the process of informing the research participants about what to expect during the experiment, the risks, any implications of the research, and obtaining their actual consent, their signature, or filling out a form saying that they want to do your study. And when an experiment involves deception, when you do have to lie a little bit in order to preserve the integrity of your experiment, it's essential that you debrief after. So you only lie to participants when you have to, and the most important thing is that at the end you tell them the truth. You don't just let them go home. You do something called debriefing, which they're doing in this picture. They sit around and explain the true purpose of the study, and they tell the truth about everything that they lied to the participants about during the study. All right, this is a very big summary slide. As usual, you do not have to watch this part, but it is a good review. I will go nice and quick. Theories generate hypotheses that are testable and falsifiable. Theories that stand up to their tests are retained and refined, while those that do not are discarded and modified. A hypothesis is a tentative and testable statement about the relationship between two or more variables. Research enables scientists to separate fact from opinion. Facts are observable realities, while opinions are personal judgments and attitudes. It's important to separate those. Those important women that we mentioned were Margaret Floy Washburn, the first woman to earn a PhD in American psychology. Inez Beverly Prosser was the first African-American woman to earn a PhD in psychology. And remember, her work was important because it influenced the desegregation laws. Mary Whiton Calkins, was the first female president of the APA in 1905. Now we'll discuss the different types of studies. There's a clinical or case study, which is observational research focusing on one or just a few people. The problem with this is low generalizability. Generalizability is inferring that the results from the sample apply to the larger population. When your sample is only one person, it's hard to generalize to the whole population. Naturalistic observation is observing a behavior in its natural setting. However, you can't control any of the variables, right? Observer bias can happen during observation, and that's when the observations are skewed to align with the observer's expectations, right? They have bias, so they might observe things differently than they really are. One way to handle this is by having more than one observer and measuring inter-rater reliability, which is the amount of agreement between observers. A survey is a list of questions to be answered by each research participant. It can be done with pencil and paper, online, or out loud. Archival research uses past records or data sets to answer research questions or search for patterns or relationships. Longitudinal research studies the same group of individuals over an extended period of time. They collect data repeatedly over an extended period of time from the same group, versus cross-sectional research, which compares multiple segments of the population at one time. One reason for using cross-sectional research instead of longitudinal would be attrition, which is a reduction in the number of research participants due to dropping out. Down to correlation. A correlation is a relationship between two or more variables. When two variables are correlated, that means that one variable changes as the other one does. But, say it with me, correlation does not mean causation, right? We don't know if one causes the other to change or not. We just know that as one changes, the other does too. A confounding variable is an outside factor that can affect both the variables you're measuring in a correlation, right? So it often gives the false impression that changes in one variable cause changes in the other. And that's why we don't determine causation from correlation. Over to the right-hand side, your R, or your correlation coefficient, is a number from -1 to +1, indicating the strength and direction of the relationship between variables. Remember, we still don't know that one causes the other. There's no cause and effect here. But the negative number tells us that as one goes up, the other goes down, and a positive number tells us that as one goes up, the other goes up. A value of 0 or very close to 0 means that those two variables are not correlated. An illusory correlation happens when people believe that a relationship exists between two things when no such relationship exists. A cause and effect relationship is something we do not see in a correlation. We only see it through experimental research. Cause and effect relationship is when the changes in one variable causes changes in the other variable. And as I said, it can only be determined through experimental research. When you do experimental research, it's important to have a random sample where every member of the population has an equal chance of being selected, as well as random assignment, where all the participants have an equal chance of being assigned to either group. You randomly assign them to the control group and the experimental group. The control group serves as a basis for comparison. They're either given no treatment at all or a placebo treatment, whereas the experimental group does receive the treatment or manipulation or medicine. A single-blind study is when the researcher knows which participants are in which group, but the participants do not. A double-blind study is when nobody knows. The researcher and the participants do not know who is in which group. A placebo effect occurs when somebody's expectations or beliefs influence their experience, and that's why we use placebos. An independent variable is a variable that's influenced or controlled by the experimenter. Sometimes it's controlled by something we can't control, right, just by life. But in a true experiment, the independent variable is influenced or controlled by the experimenter, while the dependent variable is the one that the researcher measures to see how much effect the independent variable has. Reliability is the consistency and reproducibility of a given result. Are you getting the same thing every time? Is it reliable? Validity, the accuracy of the given result in measuring what it is designed to measure. Is it valid, right? You might get the same reliable answers from your scale every time somebody steps on your scale, but if what you're looking to measure is intelligence, weighing people is not a valid measurement. A peer-reviewed journal article is an article read by several other scientists who provide feedback regarding the quality of the research and whether it's able to be replicated. To replicate means to repeat an experiment using different samples to determine the reliability, right? Reliability is consistency. Are you getting the same thing every time? If your hypothesis is really true, I should get the same results every time I replicate your study. The IRB, or the Institutional Review Board, is the board that reviews proposals for research that involves human participants, and approval from the IRB is usually required in order to move on with the experiment. I'll give you a little insider tip. Researchers do not like the IRB. Of course they're necessary, but they're often referred to as a necessary evil. It's kind of a pain in the neck to apply for the IRB approval, but of course it's necessary to protect people from being taken advantage of. Informed consent is the process of informing the research participant about what to expect during the experiment, risks, implications of research, and their official consent. And debriefing is when an experiment involves deception, lying. The participants are finally, at the end, told the complete and truthful information about the experiment. That was Chapter 2. I promise it does get more and more interesting. I think each chapter even gets more interesting than the last. So bear with me, and we're going to keep on going through these chapters. Thank you so much for watching my video, and have a wonderful day.